Today's lesson will focus on solving trig equations. I will be doing 3 different lectures for this lesson because there are several different types of examples and I want to make sure that you get them all, but you don't get bored by trying to watch, say, a 20-minute video. I want you to keep in mind that in order to solve trig equations, you will need to understand trig identities. You will need to remember your unit circle relationships. You will need to remember how to use inverse functions to solve for a variable, and all of those will come together in this one lesson. So my goal is to show you strategies on how to solve different types of trig equations. Let's begin with just a simple verification. You've been verifying trig identities this week, and I know I haven't been there with you, so we're going to try to go over these before we do any kind of quiz or test or anything like that to make sure that you guys really understand it. But if we start with this one, we want to show that cosine of negative x divided by cosine of pi over 2 minus x is the same as cotangent x. And again, this is one of those that just relies on what you already know about trig identities. With cosine of negative x, this is our even-odd property of cosine. And we know that cosine is an even function. So that means that the cosine of negative x is the same as the cosine of x. Remember that we choose just one side to work with whenever we're verifying identities, and we try to make sure they look like the other side. Now the denominator, cosine of pi over 2 minus x, this is one of our cofunction identities, and we know this as just the sine of x. And we want to show that that equals cotangent x, so I literally just bring that right side down. As a matter of fact, let's put that in a different color, so that we're recognizing we're bringing that right side down, that nothing is changing. Now you should recognize that cosine x over sine x is the same as our quotient function cotangent x, and our job here is done. So we have cotangent x equals cotangent x, and again, we have done our jobs. Now let's move on to the solving trig equations. No matter what we do in any of these examples, we are interested in solving for values of that variable. We will be recognizing these angle measurements in radians, and I will show you the solutions in 2 different ways. One, in one revolution of the unit circle, so what happens from 0 to 2 pi, and then secondly, in multiple revolutions or infinite revolutions of the unit circle, what can happen then. So if I'm looking for cosine x equal 1/2, essentially what I'm doing to solve for the variable is I'm taking the inverse cosine of both sides. We never talked about it like this before. We just kind of said, well, where does cosine equal 1/2 on the unit circle, and we left it there. But what I want you to understand is that because the inverse function of cosine and the cosine function itself, I'm taking the inverse of a function, and so those two create an identity, which just leaves me with the operator of x. So we end up with x equals cosine inverse of 1/2, and so then the question becomes, well, where does x equal 1/2? I'm sorry, where does cosine equal 1/2 on the unit circle? Well, that happens whenever we have 60-degree reference angles where cosine, or the x-coordinate, is positive. And so we're looking at values of pi over 3 and 5 pi over 3. But this is only on that domain going from 0 to 2 pi. If I wanted more general formulas, it's going to happen every time I hit pi over 3, rotate 360 degrees clockwise or counterclockwise, rotate 2 pi radians clockwise, counterclockwise, and the same will happen with 5 pi over 3. And so the way that we write it for the general solution is we say x equals pi over 3 plus 2 pi n. Means pi over 3 and then every 2 pi radians after that. Also happens at 5 pi over 3 plus every 2 pi n. Again, that's every revolution, of the unit circle. And this occurs such that n is an integer. And remember, I showed you this crazy notation before. And so this is what happens on the range of negative infinity to positive infinity. In this example, we have cosine x plus square root 2 equals negative cosine x. The goal is to get x by itself. Considering that I have x on both sides of the equations, I'll have to move this entire cosine term to join on the left-hand side with another cosine term. And I'll have to move this square root of 2 to the other side so that I can isolate the parts of the equation that have x in them, the variable that we're solving for. And so if I add cosine x to both sides, then I have 2 times the cosine of x. And then if I subtract root 2 from both sides, I have equals negative root 2. Dividing both sides by 2, this is just algebra here. Again, my goal is to isolate cosine x. So dividing both sides by 2, I have cosine x equals negative root 2 over 2. And so now the question is, where does x, what are the values of x? By, again, taking that cosine inverse of both sides, cosine inverse of this side, cosine inverse of this side, I'm really saying that x is equal to the cosine inverse of negative root 2 over 2. Excuse me. So again, for our general solution, cosine is negative in our second and third quadrants at the pi over 4s, reference angles. And so for 0 to 2 pi, I can get two angles. That's 3 pi over 4 and 5 pi over 4. And again, that's considering going from 0 to 2 pi. But if I want a more general solution, it's going to happen at 3 pi over 4, and every time I rotate back around to 3 pi over 4, whether I'm going clockwise or counterclockwise, and the same is true for 5 pi over 4. So my general solution, x equals 3 pi over 4 plus 2 pi n, also 5 pi over 4 plus 2 pi n, with the understanding that n is any integer. And again, that's my more general solution if I'm going from negative infinity to positive infinity. This example is unique in that it involves tangent and it involves squares. So we will have to think of the tangent function, but we also have to think about the fact that in order to solve for x, eventually I will have to take square roots of something. So let's begin. The goal, again, is to isolate whatever expression has x with it so that I can use some inverse function to help me solve for x. So we will begin by moving 1 to the other side through addition. So this becomes 3 tangent squared x equals 1. Then I'll divide both sides by 3. This becomes tangent squared x equals 1/3. Now, working with tangent squared is not something that we have done. But if I had a problem, for example, that said x squared equals 1/3 and I wanted to solve for x, what would I do? Hopefully you thought or said to yourself, I'd take the square root of both sides. And when I take the square root of both sides, I have to remember that there are two possible values for x. One could be positive and one could be negative. So this would be plus or minus 1 over root 3. Well, the same is going to happen over here with our tangent function. We're going to take the square root of both sides, and we will have tangent x equals plus or minus 1 over root 3. So now we have to think a little bit. How do I get 1 over root 3 from tangent? We have to remember that tangent is sine over cosine, and we have to think about on the unit circle coordinates where I could end up with 1 in the numerator and root 3 in the denominator. Now, we've been rationalizing these to root 3 over 3, but it's kind of helpful here if you just thought of it as 1 over root 3. So I would have to have something that had 1/2 in the denominator for sine and root 3 over 2. I said that backwards. Sorry, 1/2 in the numerator for sine and root 3 over 2 in the denominator for cosine. So 1/2 would have to be our sine and root 3 over 2 would have to be our cosine. But know that these can be positive or negative, so we have to keep that in mind. So where does that happen? Where is cosine root 3 over 2 for the x-coordinate and sine 1/2 for the y-coordinate? These are all of our pi over 6 reference angles. So general solution, we have x equals pi over 6, first quadrant, tangent's positive, 5 pi over 6, Second quadrant, tangent's negative. 7 pi over 6. Third quadrant, tangent is positive again. And then 11 pi over 6. Fourth quadrant, tangent is negative. And again, that gets us from 0, these are brackets, to 2 pi. So here we have a positive tangent, and then a negative tangent, and then a positive tangent, and then a negative tangent. So how can we describe this in general terms? Well, let's look at how often tangent is positive. If we start at pi over 6, I get to another positive at 7 pi over 6. That has a difference of 6 pi over 6, which is pi. If I'm negative and I start at 5 pi over 6, then I get to another negative at 11 pi over 6. If I subtract those, I have a difference of 6 pi over 6. So again, every pi. So it looks like this is happening every pi radians from a particular starting point. So for the general solution, I can write this as pi over 6, I get positive tangents, plus every pi in radians, I get to another positive tangent with a reference angle of pi over 6. It also happens at 5 pi over 6, plus every n pi. I realize I just said pi n, but that's fine. And as long as n is an integer, then we have captured all of the possible radian measures between negative infinity and positive infinity. Now remember, this was just lecture 1, so take some time, try and digest this, and then move on to lecture 2 where we'll have some more complicated examples.